We've talked about catamarans and trimarans, different hull configurations that try to solve the speed and stability problem in different ways. Hydrofoils take a completely different approach. Instead of adding more hulls, they get rid of the hull's contact with water entirely. At low speed, a hydrofoil boat looks normal. It floats like any other vessel. But once it picks up the speed, the hull lifts out of the water. It rises up on underwater wings and flies just above the surface. A conventional hull sits at the surface, pitching and rolling with every wave. The foils pass through below the turbulence. The hull barely moves. To understand how hydrofoils work, it helps to start with planing hulls. A displacement hull pushes through water. It's supported by buoyancy, the water it displaces. The faster it goes, the more drag it creates. There's a practical speed limit when adding more power, just creates bigger waves instead of more speed. A planing hull works differently. At low speeds, it floats like a displacement hull, but as speed increases, the hull starts to ride up on its own bow wave. Water flowing under the hull creates hydrodynamic lift. The hull rises partially out of the water and starts skimming across the surface. Less hull in the water means less drag, which allows for higher speeds. But even a planing hull has limits. The hull is still pushing water. It's still creating waves, and at very high speeds, the forces on the hull become enormous. Slamming into waves, structural stress, fuel consumption. Hydrofoils take that concept further. Instead of relying on the hull itself to generate lift, they use underwater wings, foils attached to the hull by struts. The foils are designed specifically to generate lift as water flows over them. As the foil moves through water at an angle, it deflects water downward. The foil pushes water down and the water pushes the foil up. The faster the boat moves, the more water gets deflected, and the more lift the foils produce. At low speeds, the foils generate some lift, but not enough to raise the hull. The boat operates normally, either as a displacement hull or, if it's a planing design, it might start to plane. But as speed increases, the foils generate more and more lift, and eventually the lift force exceeds the boat's weight. The hull begins to rise, and it keeps rising until only the foils and their struts remain in the water. The hull is flying, completely clear of the surface, supported entirely by the foils. This is why hydrofoils are so much more efficient than planing hulls at high speeds. A planing hull reduces drag by lifting part of the hull out of the water. A hydrofoil eliminates hull drag entirely. Hydrofoils show up in different forms depending on what they're designed to do. The simplest versions appear on surfboards and kiteboards. A foil attached to the bottom of the board with a single strut. As the rider picks up speed, the foil generates lift and the board rises out of the water. The rider is flying above the surface, carving turns with much less drag than a conventional board. These use surface-piercing foils. The foil penetrates the water's surface. As the board rises, less of the foil stays submerged, which reduces lift. If the board climbs too high, the foil breaks the surface. Lift drops and the board settles back down. If it drops too low, more foil enters the water. Lift increases and the board rises. The system is self-stabilizing. The rider controls it by shifting weight and adjusting speed, but the foil itself naturally regulates height. Small recreational hydrofoil boats work in the same way. Surface-piercing foils, simple mechanical systems, and no computers. They're effective in calm water, lakes, protected bays, but they struggle when waves get large. The varying depth of foil submergence in choppy water makes the ride inconsistent. As hydrofoils scale up to larger crafts, like racing yachts, high-speed ferries, military patrol boats, their design changes. These boats use fully submerged foils. These foils sit entirely below the water surface, operating at a fixed depth beneath the hull. This solves the rough water problem, because the foils are deep enough that the surface waves don't significantly affect them. Lift will remain relatively consistent. A ferry running in 2-meter seas can maintain a smooth ride because the foils are passing through water below the turbulent surface layer. But fully submerged systems need active control. Sensors constantly measure the boat's attitude and motion. A computer processes that data and adjusts the foils in real time. Hydraulic actuators change the angle of attack or move control surfaces to keep the boat level and at the correct flying height. There's also the propulsion problem. When the hull lifts out of the water, a conventional stern-mounted propeller would be too close to the surface or even break through it. So the solution is to mount the propellers on the foil struts themselves, keeping them submerged even when the hull is flying. Some designs use water jets instead. These are pump systems that draw water in and expel it for thrust, which can be positioned to work regardless of hull height. The Candela P12 is the current benchmark for this. It runs in open coastal waters at 20 to 25 knots, smoother than a conventional ferry doing half that speed. But the system is complex. Racing hydrofoils, like the ones used in the America's Cup, push the technology even further. Fully submerged foils, active controls, aggressive foil shapes that are designed for maximum lift and minimum drag. These boats can exceed 50 knots, flying a metre or more above the water. But they require skilled crews and constant adjustments to keep them stable. So, we have two types of foils here. Surface-piercing foils for calm water and simplicity, fully submerged foils with active control for rough water and performance. The idea of using hydrofoils on ships isn't new. In the 1960s and 70s, the US Navy saw them as a solution to a specific problem. Soviet submarines were getting faster. New nuclear-powered submarines could reach over 40 knots submerged, fast enough to outrun torpedoes and evade most surface ships. The Navy needed ships that could keep up. Hydrofoils seemed like the answer. They allowed high speed, the ability to operate in rough seas, and the potential for anti-submarine warfare. The Navy built several prototypes, including the USS Plainview. At 320 tons and over 200 feet long, it was the world's largest hydrofoil at the time. The Plainview could reach 50 knots foil-borne, powered by these gas turbine engines, driving propellers mounted on the foil struts. The ship used fully submerged foils with an automatic control system, maintaining level flight even in 10-foot waves. But the program didn't last. Aircraft turned out to be more effective for hunting submarines. And the hydrofoils themselves were expensive. The Navy did put one hydrofoil class into production, the Pegasus class. Smaller patrol boats designed for coastal operations, but only 6 were built, and they were retired after 10 years. High operating costs and no clear mission justified keeping them. While the military moved on, commercial operators found applications where hydrofoils made sense. The Soviet Union operated hundreds of hydrofoil passenger ferries starting in the 1960s. Designs like the Raketa and Meteor ran on rivers and coastal routes, carrying passengers at speeds that cut travel times significantly. Some are still in service today. Passenger ferries remain the most common use for hydrofoils. Predictable routes, consistent speeds, and passengers who value the smooth ride. And now, some are even electric. The efficiency of foil-borne flight makes battery power viable in a way that isn't right for conventional hulls. The Candela P12 can carry 30 passengers at 25 knots with a range of over 50 nautical miles on electric power. A conventional hull at that size couldn't come close. Racing is the other area where hydrofoils dominate. America's Cup yachts use hydrofoils to reach speeds of over 50 knots. Foiling dinghies and moths, which are small racing sailboats, have become standard in competitive sailing. The performance advantage is so significant that conventional designs can't keep up. But for cargo shipping, for naval combatants, for general-purpose vessels, hydrofoils haven't made inroads there. Their complexity, cost, and operational limitations outweigh the speed advantages for most applications. Catamarans, trimarans, and hydrofoils. All of them are trying to solve the same problem, but none of them solve it completely. The right one depends on what you're actually trying to do. Thank you all for watching. Hopefully you've enjoyed this video, and please be sure to subscribe if you'd like to see more. We'll see you all in the next video.